Log on, tune in, find out. Another good idea from Cambridge.
Today we're going to have two talks, and the first talk is by they're each going to be 50 minutes. And the first talk is by Tassos Tongas. Tassos did his PhD at the University of Patras under the supervision of Souberes, and he is currently at the University of Crete in Heraklion. He will speak about Yang-Baxter maps associated to integrable lattice equations. Tassos.
Thank you, Reinhard. So, what I would like to speak today is some recent results and some not so recent results that we obtained with collaboration with Vasilis Papageorgiou and Sasha Veselov. So, we'll talk about Yang-Baxter maps associated with integrable lattice equations. First of all, I have to apologize because I have also some introduction in this stuff, so I see a lot of experts here who have developed very sophisticated techniques for solving Yang-Baxter equation. But since some of the people in the audience are not so familiar with this say notions, I would like to remind you to say what is a Yang-Baxter map. The original Yang-Baxter equation is a relation for a linear operator R in the endomorphism of a vector product, tensor product of one vector space V. Would be an n-dimensional vector space. So it is an equation for such an operator R, but regarded as but this relation is should be regarded in the triple tensor product or this vector space V. So we have to define some auxiliary, say, vectors, maps, denoted by R1, 2, 1, 3, 2, 3, which act on the basis of this triple vector tensor product V in this way. So R1, 2 makes a summation of two indices, the first two indices in the tensor product, S1 and S2. So whenever you see two indices repeated up and down, it is assumed summation, okay? So we adopt the Einstein convention of summation of indices. And R2, 3 similarly acts on the second and the third factors of this tensor product. So if you write down now in components this Yang-Baxter equation, you see that there are 6 free indices, A, B, C, I, J, K. So because the other ones, S1, S2, S3 are summated, so you have n to the 6 cubic polynomials equations for n to the 4 unknowns. So the system is we have more equations than the unknowns, so it is overdetermined. Okay? Other forms of this Yang-Baxter equation involve also parameters, say lambda and mu, and phi can be thought as as an operation where in the set where lambda and mu take values. And we have a two-parameter Yang-Baxter equation where now zeta 1 and zeta 2 is in the original map. Okay? So, an example of such solution is given by the famous elliptic R matrix obtained by Baxter in 1972. So we have n equal to 2. So the 16 different matrix components can be put. We can put it in a 4x4 matrix, and here are the specific A, B, C, and D's. So, and the Yang-Baxter equations can be thought as the identities to fulfill the identities of this function, Jacobi elliptic function Sn. So here, lambda is essential the parameter. L and kappa are fixed parameters. K is the modulus of the elliptic curves. All right. In 1990, Drinfeld suggested that it would be interesting to consider, instead of a vector space V and a tensor product, a set, and the Yang-Baxter relation and to be thought as an equation in a Cartesian product of X, and now the map can be the R, say, operator will be just of this form here, where f and g can be thought as a set of operators in the set X. Now, the matrices Rij can be defined in this way, when I is less than j and I is greater than j. For instance, the matrix R12 is just R. R21 is R conjugated by sigma, where sigma is the permutation map. And now the Yang-Baxter equation is this one exactly, but to be regarded as an equality of composite maps in this Cartesian product, X times X times X. Well,
excuse me, in this form,
yes.
Is some analog of Turaev lemma exists that it can be reduced to representation, maybe nonlinear representation of braid group?
I'll come to the brain group of this.
So in this nonlinear setting.
Representation of the Lie group of.
Oh, in previous case you used only Yang-Baxter, which is leading by Turaev lemma to representation of braid group. Yes.
Yes.
Because all spaces V.
Well, I'm not an expert in this field, so.
The answer is yes.
The answer in that case it's also
Yes.
braid. Yes.
Yes.
Okay. Nonlinear representation.
So what Drinfeld had probably was driven by suggesting this is that such a solution will always give rise to a solution in the vector space, since a vector space naturally arises by considering the free module generated by this set X. So a graphical representation of this Yang-Baxter equation can be given as two different ways of separating a cube. So imagine now that we have on the edges of this cube, we have on the three edges here, we have assigned the values x1, x2, x3. So from this face with the R12 map, we can get x1 prime and x2 prime. Next, from to this face here, we can using the R13 map, we can find x1 double prime and x3 prime. And finally, using R23, we can find the values x2 double prime and x3 double prime. So from this data, we reach in this data here. Similarly, one can start with R13, and in the same way I explained previously, from here, R23, then here, and then here. So this path can be thought as deformed to this path here. So Yang-Baxter equality says that the final values, the star values, and the prime values are the same. Here, the end values should be the same. So, solving the Yang-Baxter equation is equivalent to solving the so-called braid relation, since these four statements are true. So if R satisfies the Yang-Baxter equation, sigma R satisfies the braid relation. And there is a close relationship between the braid equation with the Artin braid group, which is generated by n-1 elements Bi, and it is defined by these relations here. If we define a map BI-R, say, denoted by R, in this way, so R here acts on the I plus 1 component of this Cartesian product, and we make this identification here, then there is an extension of this identification extends to an action of Bn into Xn. If and only if R satisfies this Yang-Baxter relation. So solving a Yang-Baxter equation and the braid relation are equivalent problems. First examples of non-trivial Yang-Baxter maps were obtained by Sklyanin in 1988. Then in 1992, Weinstein and Xu studied these Yang-Baxter maps from a geometric point of view by using the Poissonly groups and the associated symplectic groupoids. In 1999, Tykov, Shedler, and Soloviev developed the algebraic theory of the Yang-Baxter maps, and more recently, Veselov developed a dynamical theory of Yang-Baxter maps. And in this work here, Veselov suggested instead of using this long-term set theoretic solution to the Yang-Baxter equation, this short-term Yang-Baxter map. More recent results is a classification results for Yang-Baxter map in the case where X is equal, where X is a projective one-dimensional projective space. And an example, let us give you an example of a Yang-Baxter map. So this is a Yang-Baxter map. This actually Yang-Baxter map was not known as a Yang-Baxter map, but it was called double Harrison transformation in general relativity, and was used by by people working in GR, in general relativity, to obtain new solutions from known ones for the Ernst equation, which forms an integrable system and forms the basic equation, the basic equation of Einstein fields equations. In the case we have axisymmetric space-times, or cylindrical symmetric space-times, or plane symmetric space-times. So this map was already in the literature. So what I would like to speak is a natural way to obtain such maps by studying, by using results.
It is simply two constants, yes? This letter, it means constant.
Which one?
Theta. It is
Zeta 1 and Zeta 2 are the parameters, so I'm talking about
constants, yes?
parameters. So it is. So this map satisfies the two-parameter Yang-Baxter
Okay.
equation. So how can we obtain Yang-Baxter maps in a systematic way from integrable lattice equations? So we shall consider lattice equations defined on 4 points of elementary square. Okay, so we will study such equations, and they have the fields are assigned on the vertices, and the parameters, the lattice parameters, are assigned on the edges of this square. What we use nowadays as a criterion of integrability of such type of equations is the three-dimensional consistency property, which says that we can impose this equation, lattice equation, in all faces of this cube in a consistent way. So, here it is the original equation, and when we have an additional dimension, an additional constant should be added to this picture. Okay, so what says this three-dimensional consistency property? It says that if we if we consider these initial values, the black ones, okay, and using the equation, we can, in principle, find this value here, denoted with this green. Then, from this point here, solving the equation, we can find the value assigned in this vertex, and in this square, we can using this square, we can find the value here. Next, we have two different ways of finding the values assigned to this vertex. with a red color. From this and this. There should not be a reason why these two different ways of having why these two different ways of finding this value should be the same, should lead in the same result. But if they do, we say that this equation has the consistency property.
Isn't it some, I would say, some sort of zero curvature property? To pass.
Yes, but how can we, this is almost equivalent things actually,
Yes.
because because the lattice pairs from this approach, from the consistency property, one can obtain the lattice pair. So
But in this form, it is just a Yang-Baxter relation. Right?
relation.
So why,
In what sense?
What is the reason
Exactly.
to call it?
Exactly.
You just take half
Yes.
of the surface of the cube.
Right.
So left-hand side of the Yang-Baxter,
Yes.
and the another half will be right-hand side.
Yes.
So what is the difference with
I'll try to show you that my talk will be in this direction. That I'll try to convince that these are almost the same. Are the same, okay? But in which way? So another configuration of the initial data would be this one. Okay. So the consistency property. From this lattice equation, we can. So we assume again that in all these phases we have attached in proper way the original lattice equation. So we can find the values, the red values here, by two different ways. First, we use this phase here, and then we obtain the value assigned to this vertex here. Then this, and finally from the top one, this one. We haven't used this value. We haven't go to this to the value here, which is assigned with this. Another way is using the back face, then the bottom face to obtain this, then the back face to obtain this, and finally from this on the left face to obtain this. So this is another interpretation of the consistency property, which is more well adapted to the previous, this interpretation here. So here fields are naturally assigned to the face, to the edges, to the edges, and not on the vertices.
It is called face type Yang-Baxter.
This, yes.
Interaction around the corner.
So, let us start again with an equation, a quadrilateral equation, as here, and let us view this equation as a map. So, from the values, since we will assume that we can solve uniquely on each of these arguments, so Q will be a phi linear, and moreover, we shall require Q to admit the symmetries of the square. All right. So let us assume that f on gamma can be solved uniquely in terms of these three other values here. And let us, instead of having this equation, let us view it as a map from this product, the Cartesian product, to this one. So f of delta will be fixed, and only f on alpha will be replaced by this value here, f of gamma. Just a trivial map. In this setting, we define a map with B calligraphic, say, in this way. So B will be will act on I minus 1, I and I plus 1 components of this map. So because here we have 3, 1, 2, 3, okay. So J will B is on the J minus 1, J and J plus 1 factors of the map. So key properties of this, of integrable discrete equations are this 1, 2, 3 relations here. First one says that, and this relation come at hand, most of the times come at hand. I'm completely unaware of such discrete equation of CAD graphs in which an integrable equation does not satisfy these key relations, and it can be traced back to Adler and work and the Sabat school. Okay, so the first one is an identity. It says that these Bj are identities, and this one with this one delivers this braid type relation.
This cubic relation,
Yes,
this is only braid group which is satisfied in is third one.
Yeah.
That's only braid of 3 elements.
Of 3,
exactly.
exactly.
Have any length. So I don't understand which group is it.
I'll reduce this to a set to
It looks like B3
yes, indeed.
only, yes?
Yes, it is, but it acts, so this B are in 3 times Cartesian product of X. So this is why I call it braid type. Okay, not to be the braid, say, in the braid relation. This is not a solution of the braid relation, okay? So a geometric picture of this relation here is that we have attached again values on the vertices of a multidimensional, say, path, and this consistency says that this path here can be deformed into this path here in 2 different ways. The first one says that in this square we can find a value kappa assigned to this point kappa by Bj. Then with Bj plus 1 the value on U delta prime, and finally again using Bj to gamma prime, and the other way around here, using first Bj, then Bj plus 1, and finally from this there. So this path has been deformed to this path here. So we consider 1 parameter group of transformation of this form. So it acts on X Cartesian product X3, say, and it will give us 3 new points here, and with an additional parameter, the group parameter, epsilon. So we say that if J commutes with the map here, we say that J is a symmetry of the map B calligraphic. So if we consider the B map for the discrete KdV equation, say, which is in this form here. So it is just KdV, and we have solved for one of these values. Here is, and the one finds that the most general local symmetry group of this map here is given by these three subgroups. So this one just translations in each of these variables. This is a similar translation, but it acts differently on the component on each component of the map, and this is just a scaling on x, y, and z. And this group is isomorphic, is actually the group of symmetries of Minkowski plane, isometries of Minkowski plane. So we take the first one, the first group of subgroup of symmetries, the translations, and the map associated with the discrete KdV equation. We first observe that G1 is the action of G1 on x3, x to the power of 3 is regular with one-dimensional orbits, and this guarantees that there is a two-dimensional Gaussian space with a two-dimensional space. So we can, with these coordinates, u and v, which are actually the group invariant, the invariants under the group action. Okay, so this Gaussian space, also called the space of orbits of G, is two-dimensional. If we project this map here to this space, we obtain this map BUV, where now this is naturally on the projected space. And this is the result, and this map automatically satisfies the braid relation now, the correct relation from x times x to x times x. So we have produced, we have reduced the original space to the space of the orbits. Okay, so if we twist this map, we have a Yang-Baxter map, which is also known as an Adler map. If we apply this procedure to this equation, which is a homotopy lattice KdV equation, first given by Nijhoff, Koispel, and Capel in 1983, we just solve for F2, I think, and we have this P map here, and we use this group of scalings, which commutes with the map B, and projecting this map to the space of orbits of G, which are with coordinates, where coordinates now are just fractions of x, y, and z, y, you get exactly what we called the Harrison map. Okay. In general, if we have a map associated with an n-field lattice equation, and from that map, okay, which satisfies the braid type relation, and B admits additionally a local group of G of symmetry transformations, which acts regularly on x3n with n-dimensional orbits. So we need n parameters, group parameters. Then the projection of the map to this space here will give automatically a Yang-Baxter map. Braid relation, and if we twist this, it is just a Yang-Baxter map again. The proof for this can be given by looking this scheme here. We have to note that naturally the coordinates of the Gaussian space are on the edges here, here, here. So there's a natural way of assigning the values, the new coordinates on the edges of this scheme here. For instance, let us take a two-dimensional equation, which is a specific form of a Landau-Lifshitz equation, and is given by Adler and Yamilov in this form here, where f now is this particular function. We take the B map, okay, and the local symmetric group G, which is generated by two transformations, local transformations of this form here. So again, some translations and scalings. In a systematic way, we can find the invariance under the action of this two-dimensional group here. So it will be given by these four new functions: u1, u2, v1, v2. And projecting the B map to this four-dimensional space, we obtain this Yang-Baxter map. So the method can be applied to an arbitrary n. Okay.
Tassos?
Yes.
When you go from the single set X to the nth Cartesian product,
Right.
do you see any factorization of the B map for the nth product into smaller ones for the smaller?
Well, for some maps, there is some factorization, but
in general, no.
in general, no. So the method can be also applied to more general, to the Yang-Baxter equation in higher dimensions. So here now let us consider that R is by an isomorphism from this space to itself.
Excuse me, this equation which you wrote now, does it have anything common with so-called Zamolodchikov tetrahedron equation? Very, very well known. Yes, it is. Yes, because that's I never was able to understand its formula theory. Yes, but it is something like that. Yes. I think. Yeah.
So this Yang-Baxter map in this is to be regarded as a composite of maps in X6, and you see here 4 times these 4 and the other 4, which are now where now the consistency takes place in the 8 cubes, making this hypercube in 4 dimensions. So 8 cubes. So we have such integrable systems in a cube. And this is the well-known BKP equation. So it is an equation in all 8 vertices of a cube. So if we try to find, so the most general group of symmetry transformations are generated by these 6 vector fields here. So if we take, say, the subgroup generated by V1, V2, and V3, and find the invariants which are now naturally assigned to higher order simplices than in the previous case, so now are naturally on faces. So each one of these variables x, y, z are defined on the faces of this cube. So we have six variables, and on the 6 faces of the cube. So the map can be thought as from 3 to the other 3 faces of the cube. But now, look, there is a dimensional argument here. So the total space is 8-dimensional, 8 vertices of the cube. This is a 3-dimensional group, 8 minus 3, 5. So there should be a functional relation in these 6 invariants, and that's it. This is the functional relation that these 6 invariants obey. The interesting thing is that BKP equation can be written in terms of these invariants in 2 different ways, this and this one. So we have 3 equations, 1, 2, 3 equations. We solve for u, v, and w in terms of x, y, and z, and we obtain a Yang-Baxter map, which a solution of functional tetrahedron equation found by Rinat in 1995. So it is tempting to do the same for other subgroups here. All these other subgroups that I have tried doesn't work.
Is it discrete version of BKP? Is it discrete version of BKP? Yes. It should be
sorry, the
not
lattice.
From
Yes.
82. Should be discrete version. Some he wrote.
Yes. This is a discrete lattice KP. Sorry, I haven't.
But not in this work.
So, if the equation is integrable one, and we have it admits a symmetry group, sufficient one, then we can naturally go to a Yang-Baxter map, as I showed previously. Now, but there are equations which do not admit any local symmetry group. So what we do with them? How these are associated with the Yang-Baxter map? So since there is the symmetries provide us a natural way of defining these Yang-Baxter variables on the edges or higher dimensional simplices. Now we don't have a natural way of assigning that, so this will remain on the vertices again. But we have a way of lifting this equation here in this way. So let us assume that u and we have a 2-field equation here, okay? And this and the map, the B map defined from this relation, satisfies the braid relation. Then this map here is a Yang-Baxter map. The proof is by direct calculations. So here, the new value of x2 will be y2, and the y1 is on x1. So a graphical representation is given in this scheme here. So from x1, x2, we go to p1, p2, but p2 now is identified with x2, okay? And x1, x2 goes to the black opposite q1, q2, but now q1 is identified with x1. So this combinatorial way of producing Yang-Baxter map can be applied to any lattice equation. So we have taken Adler lattice equation obtained by Hitarinta in this form. Here the parameters A and B lie on this elliptic curve. You just find this F1 and F2 maps here in this lifting of this lattice equation, a two-field equation, and you obtain this Yang-Baxter map. This Yang-Baxter map Q equation has not been previously written in a form of a Yang-Baxter map. So this is the first, say, Yang-Baxter map associated with an elliptic curve in an analog of the elliptic, say, Yang-Baxter map that Yang-Baxter equation, the Baxter equation in the for the 8 vertex model. Okay, so I'm gonna finish with another elliptic Yang-Baxter map given by Adler and Yamilov again. It is a lattice version of the Landau-Lifshitz equation. So in this map, the F1 and F2 functions are not the same as in the case of Adler equation, which we lifted on a two-field equation. And these functions F1 and F2 are given by these functions here. The elliptic curve is just a little bit different. This is the Weierstrass representation. So alpha and beta are the parameters of this elliptic curve. So the Yang-Baxter map obtained from Landau-Lifshitz equation can be written in this form here. I think, so making a synopsis, even if the lattice equation admits a local point, a local group of transformations, or if this does not admit, there is a way of writing these lattice equations in the form of a Yang-Baxter map. So thank you for your attention.
We have time for one very quick question.
Only one. Okay, so in this Yang-Baxter case, you get a two-dimensional map in your technique, several of them. Now, previously, our two-dimensional maps were of the QRT type. So what kind of map are these that you get? Are they of QRT type, or are they some other type? Are they integrable in their own right?
These Yang-Baxter maps that we have, like this one, say.
For example, some of the previous simpler ones.
Like the Adler map. Yes. The dynamics of these maps are really trivial because they are just identities. But if you couple this, together, the dynamics is not trivial. It's not trivial.
Okay, I'm afraid that because of the coffee constraint, we have to have coffee.
Still 1 minute.
No, yeah, but that clock is this is the clock. That clock is the clock. So we will thank Tassos for and anybody's free to ask him questions during coffee time.